Dear student, in this video we will discuss design compressive member procedure. How we can find out design compression as per the IS 800-2007. Before we start the procedure, in this video we can also calculate one analysis of struts, one example of design of strut, same way analysis of column and design of column. Before we start the design procedure, we know that the compressive strength of axially loaded compression member or column, it depends upon following parameters. So before we start the design procedure, we know that which are the parameters should be affect to our design. So mainly it's covered material of column, which type of material are used, cross sectional of configuration, which type of cross section we have used in our design, length of column, again we have to decide the types of effective length, support conditions, different stresses, and last one, imperfection. So imperfection are including following. So it depends on the material are not being homogeneous and isotropic, eccentric of load, and geometric of various column. So now we start the procedure of design compressive strength. In this procedure, first of all we use the clause number 7.1.2 in IS 800 page number 34. In that, the design compressive strength PD is given in a form of design compressive load. So P should be less than PD. Now what is PD? So PD is denoted as design compressive strength and PD is equal to AE into FCD. Now what is AE and FCD? So AE is effective cross sectional area that we use in a compression member and FCD is design compressive stress. Now first start with the effective cross sectional area. So what is effective cross sectional area? So the cross sectional area shall be taken as effective sectional area for all compression member like fabricated by welding, bolting or riveting. Holes not fitted with rivet, bolt, pin shall be deduct from gross area and calculate the effective sectional area. So in our gross sectional area, we deduct the diameters of hole of bolt and rivet and we calculate the effective sectional area. Next we see how we calculate FCD. So FCD is given in clause number 7.1.2.1. You can see the equation of FCD in this clause. So design compressive stress, FCD is denoted by design compressive stress of axially loaded compression member shall be calculated using following equation. Now what would be the equation? Fy divided by gamma m0 divided by phi plus phi square minus lambda square raised to 0.5 and that value should be less than or equal to Fy divided by gamma m0. This is the condition to find out FCD. Now before we start or calculate FCD, we can know about phi, lambda and FCC. So phi is also given to you in a expression form of equation 0.5 plus alpha lambda minus 0.2 plus lambda square. Now phi is, before we start the calculation of phi, we know the alpha. Alpha is nothing but imperfection factor is given in table number 7. So in imperfection factor, before we find out imperfection factor, we know the buckling class of our section. It divides by in 4 grade A, B, C and D. In that grade, we can calculate the alpha. You see the table number 7. It depends on the buckling class of column. So first we find out buckling class of column, then we find out lambda. Now lambda is non-dimensional effective slenderness ratio. The equation is given to you in same clause 7.1.2.1. Lambda is equal to Fy divided by FCC. Now FCC is nothing but Euler's buckling stress, that we know the Euler's equation of buckling. pi square E upon KL upon R square. So first we find out lambda. Before that we find out FCC. Once we find out FCC and lambda, we got the value of phi. Once we got the value of phi, we can find out FCD. Before this find out FCD, we can decide the buckling class of column and imperfection factor. Now what is imperfection factor? So imperfection factor is a constant which shift the compressive curves as shown in table, different cross section. The member with higher initial and has have lower strength due to parameters of yielding. So it depends directly the buckling class of section. Next, what is column buckling curve? So classification of different section under different buckling we denoted by 4 class A, B, C, D and are given in table number 10 in IS 800 page number 44. Now buckling class is depend upon the different section of column. Suppose you can use I section, welded section or circular section, square section, box section, channel or built up section. So depending on the this type of section, you can find out buckling class on their major axis. So table 10 is given about the buckling class of your section. The second one is stress reduction factor X and the design compressive stress FCD for different buckling class. Yield strength and effective slenderness ratio are also given in table number 8, page number 37. Table 9 in page number 40 also shows the design compressive stress FCD in different buckling class of A to D. So we can use table 10 for buckling class, table 9 to find out the stress reduction factor and table 9 to find out the FCD. Now the buckling classification curve is also mentioned in page number 35 of lambda. Curve corresponding the different buckling class are present in the non-dimensional form as shown in figure below. You can see the figure about column buckling curve and different 4 class are given A, B, C, D. So you can also find out buckling class using this figure. This is the table number 10. You can find out buckling class for different cross-sectional area that you have to design. Now we start the angle strut. So in angle strut, first we find out single angle strut. So single angle strut given in clause number 7.5.1. Now the compression in single angle strut may be transferred either concentric load or centroid through the end of gusset, or the load may be eccentrically by connecting its length to the gusset member. Now, so as per the clause number 7.5.1, two type of truss are there. First one is concentric loading and second one is load through one leg. Now what should be the concentric loading? So when the single angle is concentrically loading in a compression, the design compressive strength is evaluated as per the clause number 7.5.1. So the concentric loading is there. So we can same procedure as per the clause number 7.5.1. Second one is loaded through one leg. So the flexural or torsional buckling of strength, the single angle loaded in a compression through one of its leg may be evaluated using equivalent slenderness ratio lambda E. So in both the strut design, the procedure is same. The change is lambda. If loaded through one leg, we find out lambda E instead of lambda. Now what should be the difference between lambda and lambda E? So lambda is non-dimensional slenderness ratio and lambda E is equivalent slenderness ratio loaded through one leg. So the equation of lambda E is given to you clause number 7.5.1.2. What should be the equation? So lambda E is equal to under root of K1 K2 plus lambda VV square plus K3 into lambda phi square. In that equation, K1, K2, K3 are constant depending upon the end condition of column. Is also given the table what should be the K1, K2, K3. So it directly proportional to the end condition of column. Again, lambda VV and lambda phi is given to you in IS 800 2007. Now next one is double angle strut. So double angle strut we denoted in the 2 class, connected back to back on opposite side of gusset plate, connected back to back on one side of gusset plate. Both the case only change in effective length. So first connected back to back on opposite side of gusset plate. When we connect two angle back to back on gusset plate, the effective length of KL and gusset shall be taken between 0.7 to 0.85. Here we mention the effective length should be 0.7 to 0.85 times. Now connecting back to back on one side of gusset plate. So is given clause number 7.5.2.2. The outstanding leg shall be connected by tack bolting, or you can say tack welding, space a distance not existing 600 mm. Here we require the exceeding limit over 600 mm is given you clause number 10.2.5.5. So here we mention this limiting. Now we start first example of analysis of strut. So here two types of example are given. One is strut and second one is column. So first we start out analysis of strut. So what should be the data? Data given is determine the compressive strength of single ISI 100 by 100 by 8 at the rate 12.1 kg per meter with the length of member 2.5, ends of member are hinge. Assume that load is applied concentrically. Here you find out two things in our data. First of all, how can decide the example is analysis or design. So in analysis exam, the section is given to you. For example, ISA 100 by 100 by 8 mm. It means already you give the section size. So you have to just find out PD. It means design compressive strength. So this type of example is called analysis of strut. Here two more things are you have to find out. First one is end condition of member. Here given is both end are hinge. So for the end condition we can find out effective length and slenderness ratio. Second thing is given to you. Assume that load is applied concentrically. It means it's the types of concentrically loaded strut. So here single angle strut is given to you. So our first step, what should be the first step to find out this design of compressive strength? So first we find out ISA 100 by 100 by 8 is given to you. So first we open the steel table, in that find out area and R minimum. So area is directly you have to find out in steel table. Again the area is given to you centimeter square, we convert into the mm square. Now R minimum. So there are the two R value are given to you in steel table, RUU and RVV. It means RXX and RYY. In both the value, whichever is minimum is called R minimum. So first step we can find out area and R minimum according to steel table. Now open IS 800 table number 2 page number 18. In that we find out section classification. How can find out section classification? So three ratio we needed. First one is B by T. It means B by T, width of leg and thickness of angle. D by T, another width of leg and again thickness of angle. And third one is B plus D divided by T. So in our case B by T, here the equal section is given to you. It means B and D both leg width are same. So B by T 100 by 8 is 12.5, D by T 100 by 8 also 12.5, B plus D by T is 25. So according to table number 2, 12.5, B by T is less than 15.7 epsilon. Again D by T is less than 15.7 epsilon and B plus D by T is less than or equal to 25 epsilon. What is epsilon? Epsilon is given to you at the end of table number 2. 250 divided by Fy raised to 0.5. It means in our data Fy is 250, then epsilon value is always 1. So since all three criteria is satisfied, the section is semi-compact according to table number 2. So for the semi-compact section, gross area are taken as effective sectional area. If we found semi-compact section, so our gross area is same as our effective area. So here not find out any other effective area. We can take as the same gross area is equal to effective area. Next step, we find out effective length. So effective length we can find out table number 11, page number 45 in IS 800. Here the end condition are required. So in our data given to you, both end are hinge, or you can say pin. So both end are hinge. Effective length KL is equal to 1 times original length. So 2.5 meter is given to you, converted into the mm. So 2500 mm effective length we found. So as the member is concentrical at loading, design compressive strength calculate as per the 7.1.2. So already the given data is the loaded through concentrically loaded. So as per the design, clause number 7.1.2. So before we start the design procedure of concentrical loaded, first we find out Euler buckling stress. This equation is given to you, clause number 7.1.2, page number 34. What should be the equation? Is FCC is equal to pi square E upon KL upon R. So already we find out KL, it means effective length, and R, it means R minimum. E value is taken as 2 into 10 raised to 5. So we can find out FCC, Newton per mm square. Please remember that the value is stress. So always it should be Newton per mm square. Next, non-dimensional effective slenderness ratio. So is given to you table number 10, page number 45, lambda. Lambda is equal to Fy under root Fy upon FCC. So already we find out the value of FCC. We can find out lambda. So here the value is 1.444. Now we can find out alpha. It means imperfection factor. So before we find out imperfection factor, we needed the buckling class of our section. So for single ISA, buckling class is C. From table number 7, we can find out the buckling class from table number 7. So buckling class is C. For that, imperfection factor alpha is 0.49. Now find out lambda and alpha. We can find out phi. Phi is also given in clause number 7.1.2. The equation is given on the same clause in IS 800. Then find out X, means stress reduction factor. After find out stress reduction factor, we can find out design compressive stress is denoted by FCD. Again, FCD is a one type of stress. So value is should be Newton per mm square. Once find out FCD, the last step of our design compressive stress as per clause number 7.1.2, PD is equal to AE into FCD. So finally we found design compressive strength in kilonewton or Newton. So these are the 5 to 6 steps we can find out analysis of stress.